Let's look at another example. We must not forget that we must first eliminate all the theorems which are not in the problem. Then we are going to be left with theorems which are in the problem. We're going to use those theorems together with what we have learned in part 1. Now, here's another problem. In the diagram, O is the center of the circle. PQRS are points on the circumference. PQRS are points on the circumference of the circle, right? TOQ is a straight line such that T lies on PS. TOQ is a straight line such that T lie on PS, such that T lies on PS. PQ is equals to QR as it is shown there, Angle Q1, you can see it is equals to X. Angle Q1 is equals to X. Now, before we can even start solving this problem, we need to eliminate all the theorems which are not in the problem. Now, this is how we eliminate theorems which are not in the problem. Obviously, we must ask ourselves, are there chords? Yes, there are chords. Are there cyclic chords? They've just said that PQRS are points on the circumference. Therefore, it means that PQRS is a cyclic chord, since they are points on the circumference. Those 4 points are points on the circumference. Therefore, we do have a cyclic chord. Do we have tangents? We don't have tangents. Now, obviously, theorems on tangents are out already. Now, we eliminate theorems on chords. Is there line from the center to the midpoint of the chord? Line from the center to the midpoint. No midpoint. There's no line from the center to the midpoint. No line is not at the midpoint. It's not. It's not. We can't assume that it's at midpoint. We are never told that OT bisects PR or is perpendicular. We are never told that. So we can't assume that it's at midpoint, this line. Therefore, theorem number 1 is out. Theorem number 2, which is angles at the center, is 2 times angle at the circumference. I think it is there. I can see this angle, which is subtended by this chord. This angle is also subtended by this chord. Therefore, theorem number 2 is there. I'm going to write that in blue. Theorem number 2 is in this problem. Do we have a diameter? They've never talked about any diameter here. Therefore, we can't assume, and you can see it does not even reach there. Therefore, we don't have a diameter. Theorem number 3 is out. Theorem number 4, do we have angles at the same segment? Let's look. Angles at the same segment. One might think that this angle and this angle, they're in the same segment. But no, they are not. Look at this angle. It is subtended by this. By this, we can put a line there which is TR. We can put a TR. But look at this one. Look at which one is that? Look at this one. It's subtended by this. Therefore, this angle and this angle are not equal. Therefore, there are no angles in the same segment here. Therefore, theorem number 4 is out. We only have theorem number 2 of chords in this problem. Now, with cyclic chords, we can talk about opposite angles of a cyclic chord. Yes. So, theorem number 5 is there. Theorem number 5 is there. Theorem number 6, there's no exterior angle. There's no exterior angle. There's no exterior angle. There's no exterior angle which is going to be equals to the opposite interior angle. Therefore, theorem number 6 is out. Tangents are out. Therefore, these are the only 2 theorems which are in this problem. Now, we are told to calculate with reasons angle P1 in terms of x. We are told to calculate angle P1, which is this angle here, which is this angle P1 in terms of x. For us to calculate angle P1, in terms of x. We need to find this angle, which is O1. We need to find this angle there, which is O1. And for us to find O1, we do know this angle here and this angle there. This angle is equals to this angle. Since this line, which is the radius, and this line, it's a radius, so we've got radi, which makes this an isosceles triangle. Therefore, we can start by saying angle Q1 is equals to angle R1 equals to x. Reason, triangle ORQ is isosceles triangle. Triangle ORQ is isosceles. Why is it isosceles? Because OQ is equals to OR. Why? Because we've got radi. Radi. Now, we now know that this angle here is x. Now, we can find this angle here, O1, angle Q1 plus angle R1 plus angle O1 is equals to 180 degrees. Why is that? This angle, which is angle Q, this angle plus this angle plus that angle, they add up to 180. Sum of angles on triangle ORQ. ORQ. We know Q1 is x, plus we know R1 is also x, plus angle O1 equals to 180 degrees. Now, this is 2x plus angle O1 equals 280 degrees. Angle O1 is equals to 180 degrees. We take this to that side. It becomes O1 is equals to 180 minus 2x. They said we must calculate angle P1 in terms of x. So we got this angle, we got this angle. Therefore, we know that this angle is 2 times that angle, since they are subtended by the same chord or by the same arc. Therefore, this angle is subtended by this chord and it is subtended by this arc. Also, this angle is subtended by the very same chord or by the very same arc. Therefore, angle at the center is 2 times angle at the circumference. Angle O1 is equals to 2 times angle P1. Reason, angle at, and this is not L, angle at center is equals to 2 times angle at circumference. If we wanted, we could have said angle at center is twice angle at circumference, or angle at center is equals to, this is equals to 2 times angle at the circumference, one and the same thing. Now we know this, which is 180 minus 2x, which is equals to 2 angle P1. They said we must express angle P1 in terms of x. Therefore, we divide here by 2. We divide here by 2. Angle P1, this cancels. Angle P1 is going to be equals to, this is going to be 90 minus x, angle P1 in terms of x. Now they say to us, show that TQ bisect P angle QR. Bisecting means we know that we can bisect a line. A line, this line bisect this line into two equal lengths. Into two equal lengths. That's bisecting equal lengths. We can also have an angle. This line bisects this angle into two equal angles, into this angle and which is equals to this angle. Therefore, this angle is equals to that angle. If a line bisects an angle, if a line bisects a line, it means that this line cuts this line into two equal halves. This line cuts this whole angle into two equal angles. Now, for us to do that, we need to find Q2 to be x. Once we find that Q2 is x, we know that it is equals to Q1, which is also x. Then we have proved that TQ bisects this angle there. For us to prove that this line bisects this angle, because bisects this angle here, we start by saying that this angle is equals to this angle here, is equals to this angle here. This angle is equals to this angle there. Angle P1 is equals to angle R2, angle R1 plus R2 is equals to angle R1 plus angle R2. This angle here is equals to this angle there. That is why I say angle P1 is equals to this plus this, because it's the whole of this angle. Why are they equal? PQR is an isosceles triangle. We are told that this line is equals to that line. If this line is equals to this line, this triangle is an isosceles triangle. Therefore, base angles of isosceles triangle PQR. Why are they base angles? Because PQ is equals to RQ. Now, obviously, we know that this angle here, it is angle P1, it is equals to 90 degrees minus x. We've just got it now. Now, this angle plus this angle plus this angle equals 180 degrees. Therefore, it means that we're going to say angle P1 plus angle R1 plus angle R2, which we know that angle P1, we said is 90 minus x. Since it is equals to R1 plus R2, we know that this is going to be 90 minus x. Now, this angle plus this angle plus this angle plus Q1 plus angle Q2 is equals to 180 degrees. What I've just done here, I've just added this angle plus this angle, which is R1 plus R2, this angle plus this angle, which is Q1 plus Q2, therefore equals 180. What's that? Sum of angles on which triangle is that? PQR. PQR. But now we know that this is 90 minus x. This is also 90 minus x because this is equals to that. So this plus 90 minus x plus Q1, it's x, Q2, it's what we are looking for, plus angle Q2 equals 280 degrees. Now, these ones are going to cancel, there, cancel with that. We're going to be left with this plus this, which is 180 degrees. This cancels with that. You're left with minus x plus angle Q2, which is equals 280 degrees. We have seen in the last example that since there's a plus 180 this side and this side, these can cancel. Therefore, we're left with negative x plus angle Q2, which is equals to naught. I take this x to the other side, angle is equals to x. Therefore, angle Q1 is equals to angle Q2, meaning that, therefore, TQ bisects P angle QR. Now, we are told to show that we have just proved that TQ bisects P angle QR, where we got that angle Q1 is equal to angle Q2, which is equals to angle X. So this is angle X, and I've just said it that when this angle is equals to that angle, it means that this line bisects this whole angle. Now, we are told to prove that TSRO, it's a cyclic quadrilateral. But obviously, we know that we might have an imaginary circle somewhere there. There is my circle. Meaning that TSRO, it's a cyclic quad of another circle, not this circle, an imaginary circle. Once we prove that TSRO, it's a cyclic quad, it will mean that we have another circle where TSRO are on the circumference of that circle. That's what we've been doing in the previous examples. Now, we need to prove that this is a cyclic quad. And for us to prove that it is a cyclic quad, we know that this angle is going to be an exterior angle of a cyclic quad, which is equals to the opposite interior angle. Once we find that angle S is equals to angle O1, then we have proved that SROT is a cyclic quad. Now, we know that angle O1 is equals to 180 minus 2x. That's what we know. Now, we can find this angle there. For us to find this angle there, we know PSRO is a cyclic quad. And if it's a cyclic quad, we can say that angle Q1 plus angle Q2 plus angle S equals 280 degrees. Why? Because we've got opposite angles of a cyclic quad which are supplementary. This angle plus this angle must add up to 180 degrees. Opposite angles of a cyclic quad are supplementary. Therefore, this angle, which is Q1 plus Q2 plus this angle, S, is going to give us 180 resin opposite angles of cyclic quadrilateral or cyclic quadrilateral PSRQ. Cyclic quadrilateral PSRQ. Now, we know that this is x plus x plus angle S, which is equals to 180 degrees. And when I have 2x plus angle S equals to 180 degrees, angle S is equals to 180 degrees. We take this to the other side, which is minus 2x. Therefore, angle O1 is equals to angle S, which is equals to 180 minus 2x. Therefore, TSRO is a cyclic quadrilateral. Why is that? You must give a reason after we've said that it is a cyclic quadrilateral, because we've just proved that this angle is equals to this angle there, is equals to this angle there. Therefore, exterior angle of a cyclic quad is equals to the opposite interior angle. That's the reason. Exterior angle of cyclic quadrilateral is equals to the opposite interior angle. Exterior angle of a cyclic quadrilateral is equals to the opposite interior angle. That is why we say TSRO is a cyclic quad. And since we have proved that TSRO is a cyclic quad, then the circle which is dotted in blue is the circle that we can imagine that since TSRO is a cyclic quadrilateral, therefore it means that there's a circle there which passes through those points. I hope that this makes sense. Here's another example. We still do the same thing, eliminating theorems which are not in a problem before we can solve this problem. We first start there. Before I can even look at what the question is saying, I first eliminate all the theorems which are not in the problem. I first ask myself, are there chords? Yes, there are chords. I think there's always there are chords, but not always that there are theorems on chords, even if there are chords. Now, yes, there are chords. Are there cyclic chords? Yes, there are cyclic chords. But before we can get there, we need to read the story first. They say in the figure, XYZ is a tangent to the circle AYDBC. This XYZ is a tangent of the circle AYDCB, because that's the points on the circumference. But it's not that all these points we say they are cyclic. A cyclic quad is a four-sided figure with vertices on the circumference. So here we're saying that XYZ is a tangent of the circle AYDCB at Y. In the figure below, XYZ is a tangent to the circle AYDCB at Y. AY is parallel to CD, Therefore, this is parallel to that. Now, they say to us, AB is equals to BC. We can see it is indicated there that AB is equals to BC. This line here is equals to that line there. Now, angle A1 is equals to 26. You can see angle A1, which is this angle there, is equals to 26. X angle YA, X angle YA, which is this angle there, is equals to 74 degrees. And ADCB, ADCB, it's a cyclic quadrilateral. So it means that ADCB are points on the circumference. Now, we are told to determine the size of the following angles. But before I can determine the size of the following angles, I need to eliminate the theorems which are not in this problem. Now we know what we have. Now, we first, are there chords? Yes, they are chords. Are there cyclic chords? Since we are told that ADCB is a cyclic chord, then it means that we do have cyclic chords in this problem. Now, do we have tangents? Yes, we do have tangents. Now, we can eliminate theorems on chords. Is there a line from the center? We are not told about any center here. Is there a line from center to the midpoint or perpendicular to the chord? No. Theorem number 1 is out. Theorem number 2, do you have a diameter? We can't assume that AD is a diameter. We're not told that AD is a diameter. Therefore, we don't have a diameter. Therefore, theorem number 3 is out. I'm not sure if I did erase theorem number 2, but there's no angle at the center, which is 2 times. There's no center. Therefore, there's no angle at the center, which is 2 times angle at the circumference. Theorem number 2 is out. Theorem number 1 is out. Theorem number 3 is out. There's no diameter. Theorem number 4 is also out. Let's see. Are there angles at the same segment? No. There are no angles at the same segment. There are no angles which are subtended by the same chord or by the same arc. Therefore, theorem number 4 is out. So theorem number 1, 2, 3, 4 are out. Now, is theorem number 5, which are on cyclic chords? Yes. Theorem number 5. We don't have an exterior, at least a line if it can extend, or a line if it was extending, if this line was extending, if this line was extending, then we're going to have theorem number 6. But we can have this angle and this angle to be supplementary. We can have this angle and this angle to be supplementary. Therefore, theorem number 5 is there, since we were told about a cyclic chord. But theorem number 6 is not there because there's no exterior angle of a cyclic chord. Now, tangents, is there a radius or a diameter perpendicular to the tangent? No, there's no radius, there's no radius, there's no diameter, which is perpendicular to this line, to the tangent. So theorem number 7 is out. Theorem number 8, there are no 2 tangents from the same point outside the circle. Therefore, theorem number 8 is out. As long as there's no 2 tangents, theorem number 8 is out. Theorem number 9, obviously there's a chord and there's a tangent. Or if there's a chord and then a tangent, therefore, it will be equals to an angle which is in the alternate segment. Therefore, theorem number 9 is there. Theorem number 9. So we've got theorem number 5 and theorem number 9 in this problem. We are going to use this theorem and what we have learned in part 1 to solve this problem. Now they say to us, determine the size of the following angles given reasons. Now we are told to determine angle Y1. Now, for us to find angle Y1, we can see that Y1 is made by this chord and the tangent. And this chord subtends this angle there. Therefore, it means that this angle is equals to that angle there. That's theorem number 9, tan chord theorem. Angle made by the chord and the tangent, which is this angle, is equals to the angle in the alternate segment, or the angle which is subtended by the very same chord. Now, obviously here, we are going to say angle Y1 is equals to angle A1, which is equals to 26 degrees. Risen, ton, chord theorem. We've got our Y1. Now we are told to find angle D1. Now, we have used theorem number 9. Sometimes we're not going to use all these theorems which are in the problem, but sometimes we do use all the theorems which are in the problem. So we've just used theorem number 9 now. For us to find D1, we can use what we have learned in part 2, where this side is parallel to that side. Then we've got a Z shape here, a Z facing that way. Therefore, this angle is equals to this angle there. This angle there is equals to this angle there. Therefore, angle D1 is equals to angle A1, which is equals to 26 degrees. Risen, interior, alternate angles. Why are they alternating? Because AY is parallel to CD. CD. Now, they also said that we must find angle B. Since ABCD is a cyclic quad, we know that this angle which is D1 plus angle B, they are opposite angles of a cyclic quadrilateral. Therefore, we can find angle B because they said we must find angle B. Therefore, angle B plus angle D1, because this is a cyclic quadrilateral, opposite angles are supplementary, which is equals to 180 degrees. Reason, opposite angles of cyclic quadrilateral. Which quadrilateral, cyclic quadrilateral is that? A, B, C, D. Opposite angles of cyclic quadrilateral, A, B, C, D. Now, we do have D1, which is 26, angle B plus 26 degrees equals to 180 degrees. Angle B is equals to 180 minus 26 degrees, which obviously this is equals to 154 degrees, angle B. Now, they said we must also find angle C2. We must also find angle C2. But now angle C2, it's easy for us to find because we do have angle B. We do have this angle there, which is angle B. Therefore, we can find this angle plus that angle to be equal to 180 degrees. But we know that this angle is equals to this angle. Since ABC, triangle ABC is an isosceles triangle. Triangle ABC, this triangle, it's an isosceles triangle. Since AB is equals to BC. Therefore, we must start by saying angle C2 is equals to angle A3. Risen base angles of isosceles triangle ABC. Why are they base angles? Because AB is equals to BC. Now, we know that we're going to say this plus this, but one thing that we are looking for this angle. So most times when base angles are equal, no need for us to add this plus this plus this as we normally do even in the previous examples. And a lot of examples that I've done, I've been adding this plus that, and of which it's a good practice to do that. But in an actual fact, this plus this plus this, since this is equal to that, we're going to have 2 angle C2 plus angle B equals to 180 degrees. How did we reach this part? No need for us to even add this plus that, this plus that. No need for us to do that. But we can just know when we said this angle is equal to that angle, and we are looking for angle C2. And if we are looking for angle C2, we're just going to say, oh, since this is equal to that, then 2C2 plus this is equal to 180 degrees. But where do we get that? Obviously, we're going to get it by saying angle C2 plus angle C2 plus angle C2 plus angle A3 plus angle B plus angle B is equal to 180 degrees. Sum of angles on a triangle. But we know that since this is equal to that, I can put C2 here. That is why I get 2C2 plus angle B. But no need for us to do that. But we can just say do it, because sometimes you find that you are not going to be able to reach this part. Some of us cannot. Therefore, you can do this, sum of angles on triangle ABC. Now, we know our angle B2, which is equal to 180 degrees, minus angle B, and we got angle B to be 154. Therefore, this is 180 minus 154. We got it in the previous calculations. Then 180 minus 154, which is equals to 26 degrees, which is 2 angle C2. Since we're looking for C2, we divide by 2, angle C2 is equals to 13 degrees. Therefore, we have solved for angle C2, which is 13 degrees. Also, this is 13 degrees. We know B is 154 degrees. We know that Y1, 26 degrees. We know that D2 is 74 degrees. We know D2 is 74 degrees. We also know C1 or C2 is 13. Yes, that's what we know.